I'm Derrick Jensen. This is Resistance Radio on the Progressive Radio Network. My guest today is Charles Hall. He's a systems ecologist with strong interests in biophysical economics and the relation of energy to society. Central to his work is an understanding that the survival of all living creatures is limited by the concept of energy return on investment, EROI, that any living being or living societies can survive only so long as they're capable of getting more net energy from any activity than they expend during the performance of that activity. So I was wondering if you could talk about EROI and start on the biophysical level, on the level of plants and animals, then move to the social level.
Okay. I'll start by saying that I'm an ecologist by training, a systems ecologist. I was trained by an incredible guy named Howard Odom, and his ideas have shaped my whole life. And when I was working with him at the University of North Carolina at Chapel Hill in late 1960s, he was just beginning to transition from thinking strictly about the ecology of, let's call it nature, although, I think man is part of nature, but for the purposes of this interview, we're going to talk about humans and nature. And he was focused on mostly the natural environment, but was just beginning a transition with his book, Environment, Power, and Society, into attempting to apply these concepts to human civilization as well. And I, at that time, strictly wanted to be an ecologist, and I came up with the concept of EROI, and incidentally, you used EROEI. That's perfectly fine, but the way I use it is energy return on investment, because although we principally look at energy return on energy invested, we sometimes analyze energy return on money invested or energy return on environment invested in other such things. So what I did for my PhD work in several small streams in North Carolina, mostly the beautiful New Hope Creek, was looked at the patterns of fish migration in the stream and attempt to figure out how much it costs for them to get from point A to B, and how much they would gain in their whole life history cycle by either they or their progeny being in areas of higher available energy at the critical times of the year. And at the time, I was also thinking about salmon migrations and spent some time working on salmon migration in the Pacific Ocean as well. So I figured out from my thesis work that the fish that were migrating in New Hope Creek, and there were 20-odd species that appeared to be doing it, were getting back at least 4 or 5 calories for every calorie they invested in the migration process itself. So it seemed to be of evolutionary advantage. And I went on, and although I didn't always do the calculations, you can think about bird seasonal migration, where they invest a whole lot of money, a whole lot of energy into the process of moving from the Caribbean or South America or Central America, and moving up to the temperate or the Arctic regions to breed, where there is, for that time of the year, a tremendous surplus energy, in part because organisms that might be their competitors can't overwinter there. It's too cold. So this was the original origin, was as an ecologist and thinking about the process of animal migration, being totally fascinated by everything from various antelopes in Serengeti in Africa and other organisms there, but mostly fish. I was very focused on fish.
So just to clarify, so if you have a salmon who runs up the Columbia and then up the Snake for what, 800 miles or something. Mm-hmm. So what that is suggesting is that their progeny or the community, that the salmon run itself, because obviously that particular salmon who runs up is going to die.
Right.
But with their progeny will then gain enough energy by the food sources and other sources at the spawning grounds, and as it comes down the Columbia, to make the trip worthwhile for the salmon run. Is that what you're saying?
Let me modify that a little bit. In a basic way, yes, but the specifics are a little bit different, because you can tell that the migration is worthwhile, and I got this idea originally by actually going up to Babine Lake in northern British Columbia and looking at the salmon runs there. And the sockeye salmon that went to the ocean came back, and they were 10 pounds or so. They're pretty big fish. But some of their brothers and sisters had not made the migration to the Pacific Ocean. And those were about 12 inches long, were, half a pound at most, were much, much smaller, even though they were of the same age. And so it was clear that the salmon that made the migration were selected to be larger, and the larger salmon, the larger females, had many more eggs, and the survival and reproduction of these fish and their contribution to the next generation's gene pool was much larger. So apparently, just by looking in a pool of salmon waiting to spawn and looking at the great big sockeye salmon in there, all brilliant red and green, and the little kokanee that had not made the same migration, even though they were presumably brothers and sisters of the other salmon, you could see that there was a tremendous advantage in generating more offspring for migration. Now, in this case, the migration is out in the Pacific Ocean. In other words, the migration is downstream,
right?
Some 800 miles or something to the Pacific Ocean, and then they turn and they go up along the coast following the plankton blooms up to Alaska, so they're off the Aleutians by August.
So I was looking at it backwards. I was looking at it that the migration is upstream, but the truth is that the migration that happens for salmon, and I've worked on salmon issues for 20 years, and this is
really?
Yeah. I've been working on them. I lived in Spokane, Washington, and worked on issues of taking dams out on the Columbia and doing. Yeah. So I've been working on that for a long time. But the whole time, this is great, because the whole time I've been perceiving the migration as upstream and then like living in the ocean and then coming up just to spawn and then die. But the truth is that they were living. I mean, the migration. I understand what you're saying. This is a complete shift in my perception of how salmon live. That they are actually I live right next to a salmon stream in Crescent City, California, and the fish actually migrate out to the ocean. They don't migrate up to spawn. This is great. Thank you.
Well, great. Glad that I can talk to you as a biologist, and we can share some thoughts about that. Yeah, I mean, they have to get back to spawn, and according to the physiologist William Hoare, who I was reading when I was back in graduate school, you can tell that the salmon almost certainly evolved originally in fresh water. Essentially, they're a rainbow trout,
right.
And because they have a kidney that's most appropriate for a freshwater fish. And during the periods of glacial advance and retreat, there presumably was a large evolutionary advantage for those organisms that could migrate and go to new streams and then, but they have very, very stringent requirements for spawning. I was always interested that when they lost the Upper Adams River sockeye, for example, when they lost that particular genetic strain of fish, and then they took the dam out that had caused the loss of the fish, and they had tried to take lower Adams River sockeye salmon and reinstall them into upper Adams River, and they never took because they never had the right genes.
Mm-hmm.
And you can go on Vancouver Island, and you can go to Little Ecological River, and then you can go to, I think it's called Black Creek, just north of it. And they're completely different environments. And the salmon that live in this case, silver salmon, that live in these two environments are completely different creatures. The Little Qualicum have to be able to do well in cold oligotrophic waters, and the Black Creek salmon have to do well in warm, very nutrient-rich and plant and animal-rich environments. And yet they both do fine in their particular environments, and they are very specially adapted to their environments. And so when they put in a big hatchery at Qualicum River, and a lot of those salmon drifted into these small creeks, there was a great deal of concern of diluting the beautifully fine-tuned genetic stocks of the individual creek salmon.
Right.
We could talk about salmon all this time, but let's get on.
Well, I want to. You mentioned the EROI, and this reminds me of something that I just read not very long ago, and it makes sense, but it still was I thought really interesting. Was I was reading some work on plants, and plants we can argue about the word predict. I like the word predict, but if you don't like it, then we can just ignore that.
I'm okay with it. I'm a modeler. I sometimes predict.
Well, I'm thinking, plants predict is the point. That I was reading that plants can tell, plants in the understory grow branches by how the overstory is going to look by the time the branch gets out to where it will be able to be fully functional at receiving energy through photosynthesis. And
sure.
I thought that was really interesting because we normally, a lot of, the point is that plants are working on the EROI as well.
Absolutely. I'm looking out. I live on the shore of Flathead Lake in Montana, and I'm looking out through a pine forest, and I can see on one side of a pine tree branches that go all the way down to the bottom, and on the other side, where it's growing next to another pine tree, the branches are not there in the lower part of the pine tree. And you go there and you can find the dead branches or the little holes where the branches once were. But the tree, now I don't know whether the tree makes a decision or the branch just deals with the net, but it's expensive to have a branch, and a tree will maintain that branch only if it has a positive energy return on investment, the investment being investing into the leaves and the needles and the branches and all of the incredible chemistry and biochemistry and stuff that the branch does. But if the branch is not carrying its weight, and in a branch, like an animal, at night and during the daytime too, uses energy. It takes energy to maintain its structure, to maintain itself. It's called maintenance metabolism. And if a branch can't pay for its maintenance metabolism because it doesn't get enough weight, then it's goodbye branch. Now, whether they can anticipate or not, I don't know about that. That's a new one for me. But I wouldn't be surprised.
Yeah, if you want, I can send you the source later. But
sure.
But anyway, so how does this apply to a society? This concept.
Yeah, and I'd just like to make one point that if anybody wants to Google my name, Charles Hall, and then Tyee, Tyee, all of this stuff was written up particularly well by that magazine in British Columbia.
Okay, great.
Okay, so how did I get involved in applying this to oil and uranium and other sorts of things? Well, as I said, my advisor, Howard Odom, had got me thinking that way, and I had this really good undergraduate student. At the time, I was a professor at Cornell University, and I had a really promising undergraduate named Cutler Cleveland, and who's now made quite a name for himself in the energy world. But he came to me and said that he wanted to do a project with me, and we talked about various things, and so we decided he told me that he thought he was really more interested in energy than simply environment or ecology. And at that time, I was an ecology professor. And so I said, well, let's re-look at the Hubbard curve, and that led to us doing a paper that's called, oh gosh, I can't remember the title of it, but something like, wait a minute, I might have it right here. But that went to us looking at, I think I just found it. It was called Petroleum Drilling and Production in the United States, Yield per Effort and Net Energy Analysis. And what we did, we went back and looked at the Hubbard data. And this is published.
People might not know what that means.
Oh, the Hubbard data means how many barrels of oil you gain in the United States from drilling a foot in looking for it. This guy, Marion King Hubbard, was the originator of all of this kind of work. I'm old enough to have known him reasonably well at one time. And he famously predicted in 1955 that the United States would have a peak in oil production in 1970, and everybody shunned him and called him bad names and said he was a terrible scientist and so forth. But in fact, the United States did predict in 1970. We have never produced as much oil. Even now, with a little uptick recently, we have never produced or extracted as much oil as we did in 1970. So we took the Hubbard idea of yield per effort and how many barrels you get per foot drilled and updated his data, and we found a very strange pattern that it declined as Hubbard had observed. We were getting less oil for each foot we drilled looking for it, but then it went up, and then it went back down, and over a period of about 10 years, and this was very confusing to us. And then I remember Cutler plotting the data, and I just come back from giving my fisheries lecture in ecology, and Cutler said, look, this data, it doesn't make any sense, but it's very clear. And I looked at it, and I scratched my head, and I didn't know what. And then all of a sudden, I thought about my lecture. And at that time, Cutler was a great, big, muscular fellow, a great athlete. And I got so excited, I pounded on his shoulder with such force that I left black and blue marks. I was so excited. And I said, look at this, Cutler. It's just like for fisheries. The harder you fish, that is, the more feet you drill for oil, the less you get per foot. Your yield per effort is lower at greater effort. And, this is in economics, although economists don't talk about it very much, it's decreasing marginal return. And Ricardo, way back 200 years ago, wrote about this. But basically what it means is those people who say drill, 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 the data doesn't support what they say, at least so far, because the more you drill, the less efficiently you drill, and the lower your return per effort. And that's what we found. So we started analyzing things instead of the feet you use for drilling, the energy you use for drilling, and ultimately applied this energy return on an investment concept to getting oil out of the ground.
So they were basically measuring it by feet as opposed to measuring it by energy invested is right. Sort of like measuring what miles you get per amount of time you drive versus the amount of distance you drive. And my point is that they were kind of measuring the wrong input.
Well, it wasn't wrong exactly, but I think it's more meaningful. All kinds of things are more meaningful when you start looking at the energy investment. Well, I see what you mean. Like with the salmon, you might talk about how many miles did the salmon swim, But of greater interest, I think, biologically, is how much energy did it use for the salmon to swim from point A to point B.
Right, because if they're going straight uphill the whole time, that takes a lot more energy than if it's fairly flat.
Yeah, of course. Yep.
So, what are the implications of what you're saying? Of the last bit you're saying, what were the implications of that for the oil economy?
Well, if you plot the growth of the world economy, it's almost exactly the same curve as the growth of our use of fossil fuels. I remember hearing the mayor of Denver once say that the Sioux Indians that used to live there were completely dependent upon the bison for everything they ate, everything they lived in, everything they wore, their tools, their weapons, and so forth were all based on the bison. And they celebrated it and did dances and had special feasts and so forth in terms of the bison. And he said today, Denver is completely dependent upon oil, and not only do we not celebrate it, people don't even pay any attention to it. They think it's technology, but I mean, it drives me nuts. Right? People are talking all the time about all this wondrous technology, but almost all of that technology is dependent directly or indirectly upon having cheap energy. And how long will we have cheap energy? Well, if you plot from the end of the Great Depression till today, you'll find that the growth of the U.S. economy has declined essentially every decade, from 5% to 3% to 2% to 1% to less than 1% today. That's the growth of the U.S. economy, and in fact, of most OECD or Western economies, it's the same thing. We've basically stopped growing. Europe has basically stopped growing. Japan has basically stopped growing. U.S., we can argue about it, but it certainly doesn't grow like it used to, and probably not in real terms or inflation-corrected terms as much as 1% a year. And that's the same curve as you get from plotting the global production of oil. We used to grow. I think we could grow very much because we had a lot of energy. Economic production is a work process. Any work process requires energy. Oil is the best form of energy in all kinds of ways. And it's becoming less abundant, and I think it's happening right now. You look around, and our great universities are broke often. Most of our states are either broke or have cut back on the services they've offered enormously. Many pension plans are broke. Everybody's broke except the 1%, I guess. And so what's happening is that we have, I think, the impact of a restriction in the amount of oil and other energy, and it's a little bit more complex talking about coal and gas, but I would say the same. The declining EROI on these means that there's less and less net energy available to run our economic processes, and we're seeing that occur in the world now, and it's likely to become increasingly important.
But I read something in Forbes, I think it was in Forbes, might have been in some other sort of over-the-top pro-capitalist magazine, that said that it was saying that the peak oil myth, and I disagree with this, but I'm just throwing this out as a softball. The peak oil myth has been completely debunked.
Can I use bullshit on your radio show?
I'm sorry, what?
Can I use bullshit on your radio show?
I don't know if you can or not.
That's bullshit.
Okay, go ahead. Tell me why Forbes was wrong, or whomever it was.
Well, first of all, I'm not going to go and say I know everything and those guys know nothing. Every scientist, we're trained to be cautious and so forth. But I can tell you right now that if you took all of the oil in Bakken and you took it out of the ground that we can get out of there, that we're capable of extracting, it would run the U.S. for about a year. And we're likely not to get it out that fast. And what the new oil technologies are doing is to some degree compensating for the decline in conventional oil. And it's doing a good job. Now, whether it's going to be enough to turn the U.S. again into a net oil exporter, I look at the data and I say, just no way in hell. It's not going to happen. And we can be excited about what's going on in the Bakken, but I've been analyzing this with one of my graduate students, Egan Wagner, and when we look at it carefully, we find almost all of the oil comes out of sweet spots. The sweet spots means areas where the oil is especially thick in the substrate. But most of the Bakken and most of the Eagle Ford is not a sweet spot. And so what we find is that we're moving, we know a little bit more about this with gas than with oil. We're moving from the original areas that we started developing only 10 or 12 years ago, such as the Haynesville in Louisiana and Arkansas, in the Barnett in Texas. Those areas have already peaked as we've taken the gas, in some cases oil, out of the very best spots. The geologists aren't fools. They don't drill at random. They drill where there is the greatest concentration of oil. And if you look at the maps of where these wells are, there's a map spaced about as far as lateral extensions. In other words, the map is completely saturated with wells in the sweet spots, and there are very, very few wells in the non-sweet spots. So if we have to move out of the sweet spots, which we're going to have to do soon, then it's a whole different story, because you're going to be exploiting lower and lower quality resources. So in all of this, what we're looking at in all of this is that, excuse me, I've got this damn call waiting, and I hope, are you there?
I'm here. Yeah, I'm here.
I assume you can edit this.
So, go ahead.
In fact,
go ahead.
It's my graduate student who's working on this project who's trying to get in touch with me. But I won't answer the call waiting. I don't even know how to do it. I hate it. Not call waiting, but you know that when you can talk to two people at once.
Yeah.
Okay, so it happens to be this guy who's working on this project. So what we're doing is getting the oil out of the sweet spots, and it's marvelous technology. I'm not going to say that it isn't. I think most of the environmental impact is above ground, because it takes something like 300 to usually 1,000 giant trucks worth of stuff to do a frac job in enormous amounts of horsepower and energy to pressurize the fields, and then the fields run for only really basically a couple of years, and they decline very, very sharply in just 1 to 2 years, and then you're left with a trickle. So you have to keep drilling. It's called the Red Queen hypothesis. And in Lewis Carroll's Alice in Wonderland, the Red Queen had to run faster and faster to stay in the same place. And so if we want to maintain, or if we want to increase the shale oil production, we have to drill more and more each year, and we're already drilling like crazy.
Yeah, a couple of things. One of them is that my first degree was in physics from the Colorado School of Mines, and I took some mineral economics when I was there. And of course, the School of Mines is an entire energy school, and I remember one of the first things they taught us in the mineral economics class is the difference between regular economics and mineral economics. And basically, mineral economics is based on you have a finite resource, and what you do is you take the easy stuff first. I mean, that's
sure.
Mineral economics in a nutshell. And
so 101.
I'm sorry, what?
Mineral economics 101.
Yep. And so far as EROI, one of the things I think about with this is the Beverly Hillbillies. And at first, some of the first oil wells they were almost seeps where, like in the Beverly Hillbillies movie, they shoot a gun and oil pops up. And so there was very little energy invested. I'm just saying this in terms of people who might not be so familiar with the concept. You don't have to invest very much energy to get it out. And nowadays you have to frack, or you got to do tar sands. You've got to do all this energy. And so you're
all
getting
the Gulf of Mexico. I mean, there's somewhere between 5,000 and 6,000 of these platforms out in the Gulf of Mexico, and there isn't any steel any closer to the Gulf of Mexico than, I guess, Birmingham, Alabama, or Duluth, Minnesota. And how did all that steel get into the platforms? Well, it was an enormously energy-intensive process.
So what does this... I mean, you mentioned the universities running out of money, and of course pensions running out of money is in the news right now very much. And can you be more explicit about what you think are the implications for declining EROI? And there's a quote you have that I just want to mention, which is, if real day-to-day economics is about stuff, food on the table, a roof over our heads, things we buy, why in the world is economics taught and undertaken today as only a social science rather than a biophysical science? And so what is the relationship between declining EROI and what that question there?
Gee, that's a beautiful quote. Did I say that?
Well, it's on your website with quote marks around it.
Yeah, I think I did. That's pretty good. Yeah, well, sure. I can't believe what they teach people in economics. It's fairy tales. And you take any good economist, any honest, good economist, and you talk to him, and he'll say, well, you got to have all these assumptions to make the neoclassical model work, and this assumption and that assumption, and, we got to be selfish or self-regarding, and then you do behavioral experiments on people, and they're not. They tend to be either vindictive or altruistic, because we're social animals. It's very complicated, and the assumptions you have to make, especially relating to resources in conventional economics, are just out to lunch. And so we've attempted to construct a new economics that we call biophysical economics, and myself and my colleague Kent Klitgard, who's a very much a fully fledged economist who believes essentially everything I did, and we wrote a book together available from Springer that's called Energy and the Wealth of Nations, which is a pun on Adam Smith's Wealth of Nations. And I would like to see that used in every high school and every college that teaches economics. Let's stop teaching fairy tales to our young people. What does that mean? Is that as the energy return on investment on our most important fuels declines, then it means almost inevitably that our ability to generate wealth in society also declines. And as I stated, I think we're seeing just the beginnings of it, the first ripples on the shore of a coming storm of what's going to happen as we have less and less cheap oil available. And I think we will have not only less and less cheap oil, we'll have less oil altogether, something called peak oil. And I just got a paper accepted that looks at that in great detail. And all I can say is, if there's anybody listening to this that doesn't believe in the Hubbard curve, then you send me an email, chall@esf.edu, and I'll change you in your tracks. And with an analysis of some 46 oil-producing countries, almost all of them are showing peak and decline, production that increased, reached a peak, and declined. And that's where we are, and that's essentially where we have to go for the world. And the question is, can our alternative forms of energy take up the slack? And I see no way. Of course, we can do many things with solar and wind and so forth, but especially if you include what we have to do to compensate for the fact that the wind blows only 30% of the time and the sun shines only half the time, if you're lucky, then the energy return on investment on these things is much lower than what we've been used to. And it's required high energy and return on investment fuels for us to grow. Now, I don't think this has to be a terrible thing at all. I had a fantastic boyhood in coastal Massachusetts when we were running on about 15 to 20% of the energy that we use now. And it depends how we adapt to that. But if we try to fight it, if we try try to say this isn't real when apparently, and all the data I have indicates that this is real, then we're just going to screw things up worse. Don't forget, Mother Nature bats last.
So can we throw some numbers out for some of this, like what might have been the EROI on a oil well, just average or whatever, 50 years ago or 100 years ago? What is it now? What is the EROI on, say, solar photovoltaics? Can you give ballpark numbers for any of those, just so we get a feel for how things have changed?
No, I've written several reviews recently, and remember, all of these are approximate. We do the best we can. We're dependent upon the United States government, the Bureau of Census, maintaining good data, and there's a lot of evidence that they're not maintaining the data as well as they used to, et cetera, et cetera. But still, we got all of the information is consistent, and that is shown in our review paper. So the energy return, and the first data point we have is for 1919. That's the first year that the United States got this kind of data. And at that time, the energy return on investment for finding energy, this is going out and finding a new barrel of oil, was over 1,000 to 1.
So you put out you burn 1 barrel of oil to get 1,000 back.
Well, you don't get it back above the ground, but you find 1,000.
Okay.
Back in those days. And this is published in a paper by Guilford, Hall, O'Connor in Cleveland that was in the journal Sustainability. You can just put in MDPI into Google, MDPI Sustainability, Guilford, Hall, EROI, anything like that, and you'll find it.
Okay.
And it's open access, and as we try to do with all of our papers. And so you can, or go to my website. All your readers have to do is type in Charles Hall Energy to Google, and they'll get more crap than they can possibly deal with.
Okay.
So what we found was they got 1,000 to 1 finding oil, and it had declined by 2,000 and something to around 5 to 1 to find oil. Now, the more important one is to get oil, and that was actually somewhere around 15 to 1 back in 1919, and we actually got better up till about 1970. We got up between, depending on whose analysis you look at, somewhere between 25 and 30 to 1 to get oil out of the ground, which means you only have to use 3% of the energy that you get to get that energy. But now it's declined back down to about, it looks like it's south. It's not as much as 10 to 1 anymore. But let's say the last year is around 10 to 1. And so all countries that we've examined show that same basic kind of hump-shaped pattern, that initially the EROI is a bit lower, and then it reaches some peak, almost like a Hubbard peak, and then declines over time. And if the decline rates continue, then we're screwed, because it'll take a barrel of oil to find a barrel of oil within a couple of decades. I don't know if it's going to be a linear decline or an exponential decline or maybe something else. And I have to say that the oil from a sweet spot looks to be not too bad. Our guess at the moment is somewhere around 12 to 1 this is shale oil in North Dakota from a sweet spot. But if you get off the sweet spot, then it goes way down very fast.
And 12 to 1, you just said, is good, when 40 years ago,
it's not as good as
12
it
to 1 would have been terrible.
12 to 1 is not as good as it used to be, but it's decent. You can run a society on it. You don't need just 1.1 to 1 to run a society. We've done a lot of analysis of that, and just to drive a truck on a road takes 3 to 1, including all the infrastructure of the truck and roads and bridges. And then if you start including the infrastructure of supporting the driver and his family and health care and education and all of that, we figure that you need somewhere 12 to 15 to 1 to have anything like the civilization that we have come to expect.
So it sounds like one of the things you're asking for with the biophysical economics is for economics to take into account reality.
Oh yeah, they're out to lunch. But they write the rules, so they can write the rules and they print the money and they dump all the money from the Fed system into the banks, and they didn't bail out the homeowners, they bailed out the banks, and so the astonishing thing is that we don't have inflation. At some point it'll probably catch up to us, but it's just like these old pictures in Germany of when people would go to the store with wheelbarrows full of German marks to get a loaf of bread. We're almost doing that electronically, but it because people want to have dollars. When the world is unstable, people want to own dollars because it's the most stable currency. Then this and some other aspects are propping up the value of the dollar, and we're not having inflation. We may even be having deflation. It's quite amazing, but it could flip-flop any day, I suppose.
So, go ahead.
No, well, I don't know. You listen to people like Nicole Foss, and she'll scare the crap out of you with relation to how unstable our financial system is. And it may be, I'm not an over-the-cliff kind of guy, but it might be that we're in much greater danger of some large societal problem from the financial angle of things than from the energy angle of things, which is bad enough to begin with. A couple of my people whose analysis I respect a lot, Nicole Foss and Gail Turberg, both are really concerned. Even though they're concerned about energy, they're even more concerned about the instability of our financial situation.
Well, and one of the things that seems really central to your not biological but economic work is that the energy and the economic, or energy and finances, are pretty inextricably linked.
Of course. A dollar has no meaning without energy to back it. Gold doesn't back it, because when the Spaniards came back in the 1500s from the New World to the Old, they doubled the amount of gold in Europe, but they halved its value. It was just like printing more money. But what gave money value back then was solar light that was intercepted by the fields and the forests and the people who harvested the trees and grew the crops, and the artisans and the housewives who did all this work. The work is what causes wealth, and money is a means that we have been conditioned to keep track of it. But really what a dollar is a dollar is a lien on energy. So if you have a dollar in your pocket, that means society is willing to use about 7 megajoules somewhere to get whatever you got for that dollar. So if you buy a bagel for $1, then somebody has used about 7 megajoules on average of energy to, in this case, to take natural gas and make fertilizer in Louisiana and ship it up to Nebraska and the Mississippi River and use a tractor to spread it on the field, and then drive a harvester to harvest it, and then grind up the wheat into making you got to plant the seeds and plant the wheat, and then harvest it and grind it up and put it on a train and send it to, I guess you're in California, and then use some more electricity to mix the batter. Have you ever seen them make bagels and then boil the water? I mean, all of that's using energy, and there you pay them $1 and you get your nice bagel. But if you had no money in society, you could still trade whatever you do for bagels. You could go back to some kind of awkward trade system, and money facilitates it. But what money really is a lien on energy.
Hey, Derrick?
And that's what our Energy and the Wealth of Nations book is, and that's why we want it used for teaching. It's not that complex. You can teach high school kids this. They get it. And, of course, once the kids see this and they go into their conventional economics class and they say, what is this crap you're teaching me? What is this? Why should economics be only a social science? Where's the biophysical reality behind what actually has to happen for an economy to exist and for goods and services to be produced and distributed?
So I would like to thank Charles Hall for being on the program, and I would also like to thank all the listeners for listening. This is Derrick Jensen for Resistance Radio and the Progressive Radio Network. Thank you.